So I'm one of the very few academics attending this conference, so I will give a quick intro because most of you are probably not familiar. So I did my PhD around 1994, and I've been at Yale for about 23 years, and mostly I work on formal verification programming language. So I'm going to give a different perspective about blockchain, mostly coming from the academia point of view, or more curiosity-driven view rather than catch the next unicorn. So I actually first learned Bitcoin around 2011. I have a PhD student who has been doing research with me, and I have not seen much progress from him. And it turns out that he was building some of these ASIC mining, Bitcoin mining machine, and needless, after a while I figure out, and by that time he's no longer, interested in doing the kind of research we have been working on. Later on, we realize he's a legend in the Bitcoin community. His name is, his nickname is Fried Cat. So what Fried Cat is leaving to, what kind of research he was working on. So that's something that we have been actually working in the computer science community for many, many years. That is, we are all trying to understand the essence of many of today's complex systems. Anytime you build a Bitcoin, anytime you build operating systems, you actually need to put together all these different parts of the software and the hardware components. And then you can't just pray to the God and say your code actually works. You actually need use these, develop, find out the essence, and really understand what's going on. And so you probably have heard that in the programming language community, lots of people are developing all kinds of very esoteric theory, which people never think it will be ever useful. And at the same time, they really try to explain what is really going on in the world of various concurrent distributed programmings. So, so this is something that we have been working on for many, many years. And there's a reason for it, because we really want to understand how to build a reliable software. So the actual reason we come into blockchain world is not because, suddenly there's lots of business opportunity. In fact, last 50 years or 23 years of my own career, we have been working on how to write more reliable and trustworthy system software. And the truth is right now, none of the existing language can help you to do that. So the kind of work we have been doing is really try to understand what an operating system truly is, and if you can write some new OS that's trustworthy, how do you do it? And so you end up really understand OS is essentially building layers of abstraction. So we are not talking about an OS for your little iPhone. We are actually talking about potentially OS for any kind of device. And at the same time, you want to understand how to complexity in these operating system. And the programming language actually is the very purpose of a programming language research is to understand these and decompose them into smaller pieces so that you can actually really do it in a truly reliable way. So, so the project I have been working on at Yale for many years is called the Certikos Deep Spec project. And the goal is to build a high-assurance, hacker-resistant operating system or heterogeneous system. And there's multiple projects which I can sample a little bit, but overall, we believe the current operating system like Linux, Mac OS, or Windows, they are all full of bugs. So we need to really build a better, what we call certified system software stack in order to actually to get the kind of assurance you would need for some of these security assurance, security critical system. So what is a OS? Why we need a hacker-resistant OS? By now, everybody knows the operating system is something that runs on today all kinds of device. And of course, the actual computer system contains some application, running an OS on top of a hardware. And of course, we have heard all kinds of news that if there's a bug in the OS, then all these different applications would go wrong. So what's so special about the blockchain? It turns out that if you coming from the academic point of view, blockchain is just building a world computer. And it provides a baseline security via this so-called redundancy. You try to run the same system software on many computing nodes, and the hope is that if you attack only minority or less than majority of the nodes, then you can still reach consensus and have a correct operation. So the memory or the shared ledger serves as the state, and you use different consensus mechanism to achieve this kind of a consistency. And so that's the hardware. And the application software is just the DApps contracts you guys have heard. And of course, the main difference between this kind of software and other is they actually manipulate money. And so which means it provides lots of incentive for hacker attack. And you know, I have been working on critical system for many years, and lots of people are interested in building reliable avionics, reliable medical systems. But in the case of blockchain, there's actually huge incentive for hacker attack because they actually can get money out of it. And then, truly, for these distributed applications, you really need to make sure it's free of bugs. And what that means is you can't just have the safety. Like you write in a type-safe language like Rust, that's not going to help. You actually need a full functional correctness. And you also have to reason about the gas usage because it could be that you didn't provide enough gas or your program going into infinite loop and so on and never going to finish. So the question would be for this kind of a blockchain computer, what is the actual operating system? And in fact, all of these things that we see going on, try to provide a better scalability and so on, is all about provide various OS support on this world computer. So it could be like implementing a payment channel and implementing some plasma side chains. And so all these various abstractions you lay on top of the world computer is going to be the OS of tomorrow's blockchain. And then, of course, one of the most exciting things from the academia point of view, why blockchain is interesting, is because it's kind of a incentive-aware computing. Where actually in the open source community, we have always been talking about having everybody contribute to source code and someday be rewarded. But if you can actually associate some incentive with writing source, like tokens with it, then it will be much more exciting community because now people can see the reward and in a transparent way. And it's actually incentive can be used to provide for writing reliable code and the spec and actually even proofs. So, of course, everybody by now knows that blockchain is very vulnerable. There's all kinds of error-prone implementations. Every few weeks, you hear all these different attacks, and people lose lots of money from it. So the key challenge, as many of you probably already heard multiple times for blockchain, is the scalability and also the security. And all these techniques people are developed today for building, make blockchain scale will likely make the protocol more complex, and it will pose even additional security challenge. And furthermore, the security challenge is not really limited to blockchain itself or smart contract itself. Actually, any of these exchange server out there, that's like the great attack target, right? And the digital wallet, you guys buy USB sticks, they could have firmware that have bugs. And in fact, if we believe in incentive-aware computing, then any software, hardware components that manipulate cryptocurrency in the future has to be subject to this kind of very strong formal reasoning, and you have to make sure they are free of bugs. So that's exactly the one of the startups that I started with my former student Ronghui Gu, who is now a professor at Columbia. It's a Certik company, where we try to apply the formal verification methodology or the technique we developed to actually the blockchain community. So the idea of a formal verification is very similar to what you guys do in high school geometry class when you need to prove Pythagoras theorem that any right triangle, a squared plus b squared equals c squared. you don't try to enumerate all the right triangles. You actually mathematically show any right triangle has this property. It's impossible to enumerate the length of all the right triangles. It's infinite. Formal verification tries to divide the problem into these smaller cases and really show that it can indeed be made free of bugs. And so this formal verification community is the central aspect of the programming language research going on in the last 50 years. So we actually develop these various specification technologies and automation method to make formal verification scale. And the formal verification really, and compare with the testing, it has the benefit of full coverage, and it provides the genuine reliability. So the kind of technology we developed recently started from building operating systems. So we're trying to build hacker-resistant operating systems. And since last year, we started to apply this technology to actually the smart contract community. So let me just briefly go through very quickly some technical aspect of the technology so that you get a feel. I don't count on you guys can follow these, but the idea is that you can actually break any complex software into these very small module or components. It could be software components, could be hardware components, and the aim is just the implementation. You implement on top of a particular abstraction layer, you implement another specification, which is what your module is supposed to do, and this relationship can be formally proved using what we in computer science call the simulation. That is, the behavior of this program is exactly equivalent to the behavior of the specification. And so the simulation is a mathematical property. You can show that these two things have no fundamental difference. If the specification says, the top arrow says that's my behavior, the implementation in finite number of steps will have the same behavior. And the specification basically tries to capture all the observable behavior of these modules. And so with this kind of a little certified modules, you can actually do what we call horizontal composition. If you have two modules built at the same abstraction layer, you can link them together. And if you have a layer below that implements this, you can do the vertical compositions. And you can actually implement these verified compiler. And one of the very famous one in our community is called CompCert, which can actually show that anything verified at a C level is also verified at assembly level, and you can actually link with even the assembly code. And furthermore, you can actually handle concurrency. When you have multiple threads, you can do parallel composition with these. And so if you have an operating system kernel, which is the really complex artifacts you can imagine, we could actually verify them in a principled way by decomposing these kernel code into very small modules. So for example, operating system often have what we call the physical memory management, which you can divide them into smaller pieces, and each of these pieces is completely isolated from the other. So you can understand its behavior purely from its specification. You verify the memory management, you can verify the thread management, process management, trap handler. And after you are done, you get a verified kernel, and you can actually add virtualization support. This is a virtual machine. And by adding that, you can export the virtualization hardware interface to the process level. And once you implement this VM virtual machine support, you actually get a hypervisor. So this is how do we actually implement, decompose a very complex task that into very pieces. And this project actually was done in 1 person year. So it's much more scalable than traditional verification techniques. So we have quite a few recent papers talk about how to extend these techniques to handle device drivers, to handle interrupts, to handle concurrency. And it was actually deployed on various hardware. So this one is an unmanned ground vehicle under one of our DARPA program. And we also actually deployed it on quadcopters. So Certik is an attempt to push these technologies into the blockchain community. And of course, initially we were focusing on smart contracts. And what can be more complex than operating systems? So when we look at a smart contract, we say, wow, these codes look really simple. You don't even actually need that many layers. And of course, one of the reasons why the community only accepts very simple smart contract is because people are very worried if they write a more complex smart contract, things may not work. So the Certik initiative is really trying to provide techniques to help people get some guarantee or assurance about the kind of a smart contract, and hopefully provide the technology so that you can write actually more interesting smart contract and can actually deploy them. So we apply the techniques like labeling. We actually use manual work by verification experts to add more interesting labeling. So this labeling is to add formal specification. So a smart contract cannot be run if it does not have a specification. When you have a, if you want to say what the smart contract should do, you have to write down what is formally what it's essentially doing. And then we designed, the similar idea to decompose complex smart contracts into many layer-based specs. And then you do it layer by layer, just like what we did for verifying OS. And except the problem in this case tends to be much simpler because smart contract today is not even concurrent. So we devised a framework that helping us to decompose these proof work into a potential smaller pieces and send it to a Certik network. And hopefully we can create a community that different participants can actually help build these certified components. You can actually, some users will say, here are something I don't know how to prove. Can somebody help us prove it? And then there will be community members whose job is just doing the proof. And this is actually the most interesting aspect of the project, because now, for the first time, you can actually see you can provide incentives to write reliable softwares. So we actually have already built quite a few of these programming tools where you can submit smart contract program to the environment, and they can quickly help you, write these labels and then finding bugs. And you can actually find more detail of these demos on our Certik website. So, and in the end, the Certik tool will generate a report and tell you, how good the code is. But really, what I'm trying to actually emphasize is the technology for building trustworthy blockchain ecosystem are actually there. It's not like people are talking about it's really hard to make it secure, but there's lots of work done in my community. People are building trustworthy, avionics, trustworthy medical systems. It's just a blockchain ecosystem happened to be a really convincing killer app for formal verification because people actually care. In most other cases, at one point I was thinking, self-driving car got to be a killer app for formal verification, but it turns out most people really seems to be not care too much about their life, but everybody care about losing money. So in this particular case, we developed these smart labeling, and we have a deep spec, we have a layer-based decomposition. For those of you who are interested in our actual technologies developed in Certikos, we have a paper just presented, Rong Hui actually presented it last week at the PLDI 18, which talk about how do we build a certified concurrent operating system. But if you actually go to look at the technology, it's really building abstraction layers, certified layers of global logs, which is another way to talk about logical blockchains. So if you guys are thinking how to build a logical blockchain, laying multiple chains on top of each other, making sure they are consistent, we have the technology in that paper. And we actually used it to build a very interesting, exciting operating systems. So there's lots of work going on in my group, and many of these are more academic in nature, but I realize that most of these will have interesting implication to many of you who are servers, who really care about securities of blockchains. So we have people working on building Certikos extended with the modular Paxos, PBFT, And we are adding these incentive-aware support because you don't want people to hack how many tokens you are going to give when you see something good happens. We're also developing a smart contract language called Deep C, which is kind of like mirroring the language C. If you guys remember that operating system, even though it has been going on for many, many years, today all the OS is still written in C. So the Certikos and the Deep C is kind of try to revolutionize the way how OS should be written. And the Deep C is the programming language that we use to write these certified software. And so the certified OS really means that I can actually give you not only the binaries, and it's as efficient binary as what you would get, but at the same time you get a proof, machine checkable or third-party checkable proof that the code is indeed free of bugs with respect to the spec. So we are also building this compiler, certified compiler from this smart contract language to the assembly and the EVM. And overall, we are fascinated about this new area where people are still defining what is this world computer should look like and what is the blockchain OS and a hypervisor should look like. So I will stop right here. Okay.